So maybe now it's time for some algebra. So we've been studying the topology or shape of Bala's orientation space, but using our physical intuition, our sense of spatial orientation, and through movement. So can we capture the properties of orientation space more precisely? And maybe is there a symbolic language for communicating things like loops and homotopies in SO3? In other words, some kind of algebra of spatial orientations. And the answer is that yes, there is. So for this, we're going to really need to make use of this idea of rotations. There's a bunch of benefits to thinking in terms of rotations. First of all, they're operations. You can compose them and they form a group. And there's multiple existing symbolic ways to write them down. So maybe you've seen this matrix before. Hopefully it looks familiar a little bit. It's an example of a rotation matrix in 2D. It rotates elements of R2 about the origin by an angle of theta. How does it do this? Well, let's say we have a vector xy. We simply multiply that vector on the left by this matrix. And when we do that, when we carry out this multiplication, what do we get? We get this new vector. Drawing that out, it's just this green vector here. And how does that green vector relate to the original pink vector? Well, they differ by an angle of theta. We've literally just rotated the pink vector counterclockwise about the origin by an angle of theta. We can also rotate collections of points set in 2D space. For example, here's Bala's 2D friend, Disco, who lives in R2. He's just a collection of points. What happens if we apply the matrix to Disco? If we multiply all the different points that Disco consists of by this matrix? Well, we just get a rotated version of Disco right there. So we can also because we can think of every point as a vector and just multiply them each individually by this matrix. So the matrix can multiply whole collections, whole subsets of the plane, or even the entire plane, by this angle theta. So the really nice thing about rotation matrices is that they form a group. In other words, the product of two rotation matrices is exactly what you would hope it to be. R theta is the rotation matrix that I gave here with angle theta. R phi is the rotation matrix with angle phi. If we multiply them together, we would hope to get the rotation matrix that's by an angle of theta plus phi for any angles theta and phi. And what do we actually get? Let's work it out. If we multiply these two matrices, if we use matrix multiplication, we get this new matrix with these 4 entries. It looks a bit scary maybe, but if you remember from trigonometry, your angle sum formulas for sine and cosine, those are exactly what we're getting in each of these entries. So in fact, this is exactly cosine of theta plus phi, negative sine of theta plus phi, sine of theta plus phi, cosine of theta plus phi, which is exactly the rotation matrix corresponding to the angle theta plus phi. So that's great. So we really do get that the product of two rotation matrices is the rotation matrix of the sum of the angles. Okay, so for 2D, that's the situation with rotation matrices. They work perfectly well. And what about in 3D? Well, there are 3D rotation matrices, 3D versions, and here are 3 specific examples with respect to the x, y, and z axes. Rx of theta is given by this matrix, for example. And let's just take a look at that one in particular, for a second. So notice that it looks a lot like our 2D rotation matrix over here. And over here, it's just holding the x-coordinate fixed, which is a good thing actually, because if we imagine a rotation about the x-axis, that's exactly what's happening. All the x-coordinates are held fixed. The y and z coordinates are the only ones that are changing. And those are changing in the same way, essentially by a 2D kind of rotation in every plane that's perpendicular to the x-axis. So that's exactly what this matrix is doing. It's holding the x-coordinates fixed. It's rotating each plane perpendicular to the x-axis by the same old 2D rotation matrix in those yz coordinates. And we're doing similar things with this and this rotation matrix. So these 3D ones are actually not that hard to unpack and understand. And they do obey the right-hand rule. So when you have a positive theta, you can just imagine pointing your finger in the positive x direction, and a positive theta will curl bala, in this case, in this direction. In this direction, if we apply this matrix to bala. So they're nice. There's a lot of good things about 3D rotation matrices. But these are three special examples, rotation matrices with respect to the x, y, and z coordinates, axes rather. What if we want to look at axes besides x, y, and z? Do we have rotation matrices for those? Well, we do, but how are those going to look? Are they going to be nicely behaved, or are they going to be more difficult? Well, basically rotation matrices, as great as they are, they do have some drawbacks, and this is one of them. So this is an example of a more general rotation matrix whose axis is not x, y, or z. And first of all, there's 9 parameters, even though the set of rotations is just 3-dimensional. So that's already a little bit annoying that there's 9 parameters to deal with. But in my mind, what's more annoying, what gives more of a headache, is that it's not very apparent at all what the axis of rotation is. And one has to do a lot of work to extract the axis of rotation from this matrix that I've drawn here. And similarly, the angle. One has to do quite a bit of work to extract the angle. So these basic geometric properties of a rotation are not apparent from a 3D rotation matrix, unless you're in a very special case like a rotation about x, y, or z, in which case it's easier to figure out. So that is a drawback. But luckily, there is another option.